This is the solution to question 7.8, which is in the hydrostatics chapter of the FEEG1003 thermofluids workbook. As ever, usual caveat with these solution videos is the minute you think, or if you've got stuck with a question or got the wrong answer, the minute when watching the video you think you've got a bit of a clue of how to do it correctly, pause the video, keep going, see if you get the right answer. If you still don't, unpause it, keep watching, etc. Okay, so don't burn through the whole full work solution and then pretend you could have got it in the end. Okay, so try and use these videos most effectively by pausing them if you think you've got enough additional information to carry on where you left off. Okay, let's have a look at the question. So here it is. First rule of problem solving club is to read the problem and underline all the important bits. The second part is to draw a diagram. Now the diagram is already here. It's not complete though, because we need to label it. So just looking at the question, an air, water, oil system is shown in the figure. The oil's got a relative density, so we need to underline that. We need to understand what relative density is, or specific gravity. That's the density relative to that of fresh water. Density of fresh water is 1,000 kilograms per meter cubed. So we need to multiply that value, 0.785, by 1,000, and then that gives us the density of the oil, so 785 kilograms per meter cubed. Okay, the whole system's open to the atmosphere, and in this case we've been given atmospheric pressure as 0.98 bar. So we also know, because it's in bar, we need to get that into Pascal, so we need to multiply that by 10 to the 5, don't we? Okay, so that's the next thing we need to do. Here's the question itself. Find the pressure of the enclosed air. And then we've got some extra data there. But find the pressure of the enclosed air. It doesn't say absolute or gauge pressure. So we can work out either, as long as we state what we've worked out. Okay, so in this case, I think we'll work out the absolute pressure of the air, just because. So we need to add on atmospheric pressure, which we've been given on this side. So in a way, it's kind of implied that we need to find out the absolute pressure of the air, but we should always state whether we've calculated a gauge or an absolute pressure. Right, finally, last couple of things. Given the air-water interface is 10 centimeters above the oil, so that's 0.1 meters, because we're going to work in SI units, and the depth of oil is 1.2 meters. Okay, so we've got quite a lot of information in there. We've read it very carefully. Now, there's our diagram, so we're going to add in some extra bits if we can. Let's just make sure this works. There we go. Okay. Oh, excellent drawing, if I do say so myself. Right. The air-water interface is 10 centimeters above the oil. Okay, so that in there, this is where the drawing becomes less professional, is 0.1 meters. And the depth of the oil is 1.2. And here we have atmospheric pressure. Okay, that's what we need to find. Pressure of this bit here, the air. And we've also got the density of this as well. So that's 785. Oh dear, there we go. Okay, and we know that the density of water is 1,000 kilograms per meter cubed. So we have everything in place. So now we're going to go over to the whiteboard and solve this. I'm going to show you the correct way. I'm also going to show you a slightly different way, which is incorrect, but almost gives you the correct answer. And I'll explain why we shouldn't do it the incorrect way, and why it almost gives us what looks like the correct answer. Okay, so over we go. Okay, I've drawn it on the board, and this is the methodology part of solving the problem. So we've read the question, we've drawn a diagram, now we need to figure out, with the knowledge that we have, how to solve it. This is effectively Manometer Club, so you need to go back to the lecture and the 2 rules of Manometer Club. The first rule is that pressure is equal along a line that defines the lower boundary of 2 immiscible fluids. Another way of looking at this is that we cancel out the bottom part of the manometer where all the fluid is the same. So if we look at the diagram, the lower boundary is actually, well, I'm going to draw this red line. Because that means that we can delete everything in this hatched area. Okay, that's all water. So the pressure here and here is equal, and it gets deleted. The second rule of Manometer Club is that pressure at a point equals the sum of opposing pressures. Gravity is acting vertically downwards, so the pressure of those 2 red dots has to be the same. It's static, nothing's moving, there's no dynamics here, so it's simplified. So that will allow us to write an equation to solve for the pressure of this air. Right, so on both sides, we've got the pressure of the air plus this little bit of water here, so rho times G, so rho water times G times 0.1 meters, equal to atmospheric pressure plus the pressure from this oil, which is the density of the oil, times G times 1.2. Okay, so now we can rearrange and substitute in the values. So the pressure of the air is equal to the atmospheric pressure, 0.98 times 10 to the 5. And if we put that into Pascal, we converted it from bar, plus the component of the oil, so 785 kilograms per meter cubed, which is the density we've been given, times G, 9.81, times its depth, 1.2, and then minus this little bit of the water. So 9810, which is the density times G, times 0.1. That gives you the answer in the book. Okay, there's a different way you could do it, which is incorrect, and that is by not drawing a line through the lower boundary of the immiscible fluids. So you could actually draw it here. So right through the boundary between the air. So the pressure of the air now, this might seem easier because we think we can just get the pressure of the air by adding those two together. Pressure at point is equal. Okay, so we know that is 0.1, so we can take atmospheric pressure, and then add on the 1.1 metres of oil above it, that should give us the right answer. Well, ironically, it gives us a pretty close answer, but it's not the correct methodology. So here, you would say that pressure is equal to the atmospheric pressure, 0.98 times 10 to the 5 plus 785 times G times 1.1. Okay, and that gives us a very close answer, 106.47 kilonewtons per metre squared. The reason it's so close is because the relative density of the water and the oil is quite close. But the methodology is incorrect, it's flawed. If there was a larger difference in the densities, the difference between these would be much larger, and the error would be a little bit more apparent. As it stands, it looks like that you've just done some rounding or added some extra decimal places, and that's accounted for that difference. That's incorrect. So you have to draw it through the lower boundary. It gives you an additional term, which is this one, but it's the correct and only way of doing it. And that's, again, just to reiterate, that's because everything below this lower line is all the same fluid. So the pressure here is the same as the pressure here. So we draw that lower line because it makes the problem simpler. Okay, we could have taken pressure here and here. We would have had an extra term on each side, which was this bit. Okay, but we've drawn it through the lower line, which simplifies it. It deletes this. If we draw the line higher and incorrectly, it makes it seemingly even quicker, but it's the incorrect way of doing it, because you're not deleting equal pressures below this line now. You've got this distance of water, and then small distance of oil, and then that distance of water, and that's where the error comes in with this answer. Okay, so that's the way to solve the problem. Again, you need to know your manometer club rules, and you need to know that pressure is equal at a point, and then it's just the sum of the opposing pressures. It's static, nothing's moving. It's the beauty of hydrostatics. So we just have a nice simple equation with just the one unknown, which is the pressure of the air.